So this is the back side of your gold sheet, and these difunctional compounds that we're going to look at on the back side are compounds that have two nucleophiles in the same molecule reacting with uh, another molecule where there are two electrophiles in the same molecule. And so obviously we can't form a ring now because a nucleophile can't form a bond to a nucleophile and an electrophile can't form a bond to an electrophile. So in the case where we have a dinucleophile and a dielectrophile, then we will only get polymers. So here I have lined up a dielectrophile next to a dinucleophile, and well, actually what I started out doing here is showing you one monomer reacting with the other monomer, the dinucleophile forming a bond to the dielectrophile. And so I have formed this dimer, and so this is the dimer that has the dinucleophile now covalently bonded to the dielectrophile. So now we have this dimer that at one end has a nucleophile that could react, and the other end has an electrophile that can react. And so the nucleophile can react with the electrophile of a neighboring dielectrophile, and the electrophile can react with the nucleophile of a neighboring dinucleophile. And so then we end up having this tetramer, dielectrophile, dinucleophile, dielectrophile, dinucleophile, all attached to each other. And then we can again represent that as a polymer by putting parentheses around the repeat unit. So if we put their first parenthesis here, then we'd have this dinucleophile bonded to the dielectrophile, then it would start over again. So we put the parenthesis before where it would start over, and then we'll put the subscript N, and that would represent the polymer. And so this is then what it looks like to make a polymer out of that has a repeat unit that is made from two different monomers. Okay, so much bigger repeat unit than what you saw in the previous example. And the context of this is we just learned about epoxides and reactions of epoxides, and so we learned about epoxides, we've heard of epoxy resins, and so these are the molecules that actually are used to form epoxy resins. And so it's interesting because this is not a symmetrical molecule. We have an epoxide, which you know is an electrophile because it pops open and has a partial positive carbon on it, and then at the so that's between two carbons, and then the third carbon has a halogen attached to it, which you also know is an electrophile because that is a leaving group. So this is our dielectrophile that is called epichlorohydrin, and then we have another compound called bisphenol A that looks like this, and this is a carbon in between with two methyls attached between the two benzene rings. It's a diphenol, and if we add 2 moles of sodium hydroxide, we deprotonate both ends and make it a good dinucleophile. So this dinucleophile then will react with this dielectrophile, and one end can react with this end that has a chlorine on it, and then another similar molecule can react with the epoxide end. So this can add there and pop that open. And it gets pretty complicated quickly because this is unsymmetrical, and I have a handout where I've kind of summarized this, and I'll see if I can get that to you. But this is the classic way to make a epoxy resin using bisphenol A and epichlorohydrin. Up here on the side of your handout, I have drawn a fragment of a polymer, and I have identified the different parts of the the polymer. And this should look familiar to you because we've talked about reactions of epoxides and what the products look like. So if these alcohols here, there's the alpha carbon, and then the neighboring one is the beta carbon that used to be, this used to be an epoxide there, and this used to be an epoxide there. So we attacked with some sort of a nucleophile here, an oxygen nucleophile attacked there and popped the ring open. And so this is, I've drawn this fragment and I've circled the units here, and you see there's two different kinds of units, and if we separate them out, then this would be a deprotonated alcohol. That's your dinucleophile. And then I'm going to number this just so I make sure I get this right here. So 1, 2, 3, 4, 5, 6, 7. So the dielectrophile originally was 7 carbons long. 1, 2, 3, 4, 5, 6, 7. And between carbons 1 and 2, there used to be an epoxide, and between carbons 6 and 7, there used to be an epoxide. 1, 2, 3, 4, 5, 6, 7. And so this dielectrophile is going to react with this dinucleophile that is going to be formed by the 1,3-diol reacting with sodium hydride to deprotonate it. Okay? So this is one example of making a polymer by using a dinucleophile and dielectrophile. So in the next video, we'll look at the purple polymer practice sheet, and we'll work through a couple of those making polymers, and then after that we'll look at some examples of polymers and thinking backwards, what were the monomers that were used to make those particular polymers.